is this is where we can start using people. Okay? So, suppose A and B are fixed. So we're walking to a specific point. Okay. Then what we can do is we can say the walks to AB with steps in S equals the union S, little s belonging to capital S of the walks to AB minus S concatenated with S. Right? So what I'm saying is, if we walk here, right, so suppose we have a walk that ends up at this point. Well, so the final step of that walk is going to be some little s belonging to capital S, and then the previous walk, this belongs to WAB minus S. Right? So what I'm saying is we can sort of recursively enumerate these walks, right? Any walk to AB is a shorter walk followed by one more step, right? Does that make sense? Right. So we can recursively enumerate the walks, and so we can also recursively find the generating functions. Okay? So this is going to be something like the generating function walking to this point is going to be some kind of linear combination of the generating functions to the previous points. Right? I mean, just that's kind of what we're doing. And then we can make a Maple procedure to do that. Okay, so any questions about the general idea? So if we fix AB, then we can find the distribution of A1 over walks to AB. Right? So if I know the point that I'm walking to, right, then we can find everything we want about the random variable that's the number of losing times, right? And of course, it doesn't really depend on the number of losing times. So this program that I made, I mean, if you want, you can look at the number of sign changes or the number of times we visit y equals x and so on, right? So any questions about that? So now remember, the original question was asymptotically what's happening. So if I'm walking out really far, we want to know what does the distribution of these statistics look like, right? So now we can compute for many AB. Now we can estimate the asymptotic behavior. Okay. So, for example, what I'm working with now, what the program does is like what I showed you before with the other example. So we're actually looking at n comma n. So now we're walking to the diagonal, right? And we have an arbitrary set of steps. And so we can say, okay, what if I walk to the point 100, 100? And then so we have our random variable, the number of times we go below the line y equals x. So we can compute that distribution. Then we can walk out even further and compute the distribution, and so on. So we have a bunch of distributions with all their moments, and then we can try to see what do they limit to. Okay. So let's see how much time. Oh, okay. So I don't think I'll show you. So the program is online, right? But so the nice thing about this program is you can give it any step, right? So of course it's slow, and you can't give it. So I think I worked it with like a set of maybe size 5 or something like that. And so what it does is it computes a bunch of theorems, right? So if you take it, so I give you a set of steps. For any subset of that, you have a certain theorem. So for example, if I have the steps 1, 0 and 0, 1, then in the limit, the distribution of this random variable behaves like this, right? So for each set of steps, you have a certain theorem, and this is going to output that theorem. So
did you try a directed queen and a directed king?
So by directed queen, that would mean like
you can go from one step to anything.
Anything? Well, no. So it has to be a finite set of steps, right? So this I can't handle something like that,
Okay.
right? But I mean, so it could handle something like maybe you can go like a knight. You know, you can go like 2 and then 1, or something like that. But it can't handle an infinite amount of steps. So you have to pass it a finite set of steps that you're allowed to do. Okay. And yeah, so let's see. So it deals with that. And so now the thing is, so it's not like, you know, we dealt with when the step was right or up, we dealt with king, so now this is, you give it anything that works with it, right? So that's nice. Of course, the thing is, it's just a asymptotic, right? I mean, so it's just numerical. So what it does is, so for each moment, maybe I should write it down. Okay, so you compute moments as function of n. You know, maybe n will be 100, 101, and so on, something big. And then you're going to guess in terms of some kind of ansatz. Okay, so the ones we use is, I think, for the expected value, we expect that to behave linearly. The variance, like n squared. And then, and then after that, we go by the centered standardized ones, which we expect to stabilize to a constant when n gets big. Okay, so the thing is, of course, this is all guessing, right? So we don't really rigorously prove anything, right? But, so, I mean, this does give us an idea of what we think happens. And so the nice thing is we tested this on the thing we know with where we're just stepping to the right and up, and we end up on the diagonal. And so I showed you we know how to find the moments in terms of n in that case, and they agreed, you know, pretty well, like to a few decimal places. They gave us the right thing. So that was nice. So it does work in the case that we can verify, so hopefully in the case that we can't verify, it gives us something interesting. Okay? And so let's see, the last thing I want to do is what if you have more dimensions? So the nice thing about this recursive kind of thing is you can apply it to any amount of dimensions you want. So, for example, let's just look at 3 dimensions. So, for example, in 3 dimensions. So now we're going to have our walk. So we're walking around in 3 dimensions. And say we can only, well, just for now, say we can only go 1 step in the x, y, or z direction. So now this time we have a bunch of different regions, right? Instead of like a losing region and a winning region, we have, well, we could be in the region x is less than y less than z, or we could be x is less than z is less than y, and so on. And so we have those regions, and then sort of like a boundary region, that we just call that like none of the above. So altogether, that's going to give you 7. So in this case, there's a walk is going around and it visits these 7 different regions. We can ask questions like, what portion of the time is it in the first region, and so on. So in this case, you could come up with your generating function, and there would be 7 different indices, 7 different things to keep track of, and you could find estimates for how distributions of those variables work out. Okay. Yeah, so I mean, right now this is sort of still, I mean, it's just a little project, right? But I think the main idea here is that, you know, sometimes, you know, very special cases have their own symmetries that you can work out with on paper. But if you add a little something different, you make it asymmetry, then you don't know what to do. And so like I said in the abstract, in this case, some numerical stuff, and Maple was able to help us out. So thanks for listening.
Let's thank the speaker. Maybe we have time for a question or two.
You could try the cycles too. I mean, you've got an underlying directed graph,
Okay.
which you're not allowing any cycles. But if you
Right.
had cycles, you could use the same recursive technique.
Okay.
There's a technique called signal flow graphs.
Okay.
Graph theory for eliminating circuits.
Okay. So I haven't heard of that, because the same technique will give you, it would just keep going, right? So there's some kind of way you can modify that, you mean?
You get a recurrence.
Okay.
You somehow build in the number of steps you've taken, yeah? You can see build in like the number of steps you've taken in your total walk?
Yes.
Okay.
He's got that in there anyway. That's C, isn't it?
I thought it was kind of where we landed. It was easier to know.
Maybe you need another variable.
Right. And then sometimes it can specialize to one or something.
Yeah.
Any more questions? Let's thank Anthony again.
No.